to everyone. So, in these lectures now today we will talk about the thermodynamics of gaseous nitriding in particular, but for that we will also look at the general gaseous phase thermodynamics and the gas solid equilibrium thermodynamics. So, for that if we want to first look at actually the thermodynamics of gaseous reactions, which we have discussed briefly in the last class. Now, we will take a particular reaction which is of more importance for us in the context of nitriding and see actually how we can apply the equilibrium onto these reactions. So, for the dissociation of ammonia gas, it goes into nitrogen and hydrogen. So, this reaction is very important because of considering the huge importance of synthesizing ammonia. That means this reverse reaction is very difficult. So, it requires a lot of effort, whereas the forward reaction, that means dissociation of ammonia, happens quite naturally. That already implies that it is a very unstable compound, ammonia. So, now for this reaction, if we want to understand what is the equilibrium. So, what are we interested in this? For example, we have a reaction chamber in which we have introduced 1 mole of ammonia and we have maintained it at a constant pressure. Okay. Let us say that we have maintained it at a constant pressure, like this kind of a piston and a cylinder combination. By controlling these weights, we know that we have maintained the constant pressure and we have kept it at a constant temperature by placing it into a furnace which is maintained at that temperature. Now, we know that such a reaction runs once the ammonia is placed inside, and then finally we end up with, in this system, ammonia molecules, N2 molecules and H2 molecules. Now, what will be the composition of this gas mixture for the given temperature and pressure? Okay, that is what we would like to know. That is what we can achieve from the equilibrium thermodynamics. So, how we can do that in this particular reaction is, for at equilibrium, delta G of this reaction should be equal to 0. Now, how we can look at that? The Gibbs energy is actually a state function or a energy function. So, which depends on the temperature, pressure and the composition of the system. Now, here we are looking at this reaction at constant temperature, constant pressure. So, that means we are only looking at what would be the composition at equilibrium the system wants to have. So, that is what is our objective. So, now when we have a mixture of things in a system, that will have as a mixture a certain value of Gibbs energy, and in that mixture all these individual components carry some amount of Gibbs energy, that is called the partial molar Gibbs energy of the species. So, that is nothing but the partial molar Gibbs energy is nothing but the chemical potential. So, it is called either partial molar Gibbs free energy of a component or chemical potential of a component is one and the same. So, we use this partial molar Gibbs energy with a bar on the top of the species. So, for example, for this reaction, for the delta G to be 0, then partial molar Gibbs energy of ammonia, that is represented by this bar. If this is not there, that means it is the Gibbs energy of that system, should be equal to half of partial molar Gibbs energy of N2 plus 3 by 2 partial molar Gibbs energy of H2. Now, if we write down what would be the value of actually the partial molar Gibbs energy of a component, that is always given with reference to a reference state. So, this has been I have explained this in the last lecture how we choose a reference state. So, now for that reference state value of the this chemical potential is given by with the symbol naught on top, okay, and then NH3. Now, this is about the reference state. Now, actually with reference to that, in the actual mixture what we are considering, what would be its Gibbs energy, that is given by the RT ln partial pressure of NH3. As you can see that by telling about the partial pressure of NH3 in a gas mixture, that means we are connecting actual composition of the mixture with the chemical potential. That means in the this value remains the same, but depending on the magnitudes of these three constituents in the system, this value can change. So, that is how the chemical potential would depend divided by P naught. Now, this P naught is actually coming from the way we defined the pressure dependence of this quantity at any given temperature. So, that means this value is defined the G naught NH3 for this value of pressure. So, similarly we can write for the N2 G naught of N2 plus 1 by 2 RT ln partial pressure of N2, again the reference pressure, and then plus 3 by 2 G naught of H2 plus 3 by 2 RT ln partial pressure of H2 divided by the reference pressure. So, now we are writing the chemical potential of the ammonia here, and this belongs to the chemical potential of the nitrogen, and this is actually representing the chemical potential of hydrogen. Now, if we rearrange these terms, G naught of NH3 minus half of G naught of N2. So, all these reference state values of the Gibbs energy or the chemical potential, we are moving it on one side, minus 3 by 2 G naught of H2 equal to, now we move this RT ln P NH3 by P naught to the right hand side, that will become half RT ln P N2 by P naught plus 3 by 2 RT ln P H2 by P naught. So, I will erase this portion now. So, this will be now these two quantities and taking this on the other side, minus RT ln P NH3 by P naught. And if you rearrange these terms, that means using the mathematical relation ln m minus ln n equal to ln m by n, and then if we impose that here, then we get RT ln H2, and now all these stoichiometric coefficients will go on to the power. And this is a negative quantity that we are adding up, that will be partial pressure of NH3. Now, we have all the reference state pressures, that will be P naught power half and P naught power 3 by 2, that will be P naught square. Yeah, so, that would be P naught minus half, P naught minus 3 by 2 into P naught, that is equal to P naught power 2 minus 2 plus 1, that will be P naught power minus 1. So, this is what we can represent now all these quantities together. Now, we need to define what is the reference pressure. Suppose we have chosen this reference pressure was given for all the gaseous species. For ammonia we have chosen for N2 as well as H2. For all these cases, if we choose the reference pressure as 1 atmospheric pressure, and then this quantity actually is the standard Gibbs energy of this reverse reaction of this, right. So, if we write the standard Gibbs energy of this forward reaction, that would have been the standard Gibbs energies of this products minus the reactants. If it is the other way around, that means it is minus delta G naught of this reaction. So, that is how we can write that delta G naught and then this minus symbol to the other side. So, if you look at this quantity here, that is actually the equilibrium constant. So, by that we write that delta G naught equal to minus RT ln K. Okay. So, this is the kind of relation which you can use all the time whenever we have a equilibrium of the reactions. So, now how we can get these values, for example. So, the delta G naught, it is coming from the standard Gibbs energies of the species in their reference state. That means, if we have known the values of Gibbs energies of ammonia gas and N2 gas and H2 gas as they are in a pure state, then we will be able to compute delta G naught, but we need to know these values as a function of temperature for a given pressure. So, delta G naught is represented as delta H naught minus T delta S naught, that is equal to minus RT ln K. So, now if we take that to the now what we are writing is that delta H naught minus T delta S naught equal to minus RT ln K. Now, for any given temperature, so we need to know the delta H naught and delta S naught. This can be obtained if we know the specific heats of the gases involved, then one can calculate the enthalpy and entropies, then one can actually get the delta H naught and delta S naught. But for most reactions, delta H naught and delta S naught have a very weak dependence on temperature. That means, we can treat them as constants for a given pressure at a range of temperature. So, that means, by treating them as constant delta H naught and delta S naught, that means they do not change with temperature. So, then actually we can say that these quantities can be written as delta H naught by RT plus delta S naught by R equal to ln of K. So, what we can see is that this quantity is a constant if we say that as a beta. So, that is a beta by T plus if I give this quantity as a alpha as a constant equal to ln of K. So, now we need the values of this beta and alpha to know the equilibrium constant of a particular reaction. So, from where we these values are already measured and are tabulated for most important reactions, as one can see here in this table. Okay. For the details one can refer to this source. So, it is a edited book with Mittermeier and Somers as the editors, and it has got all the fundamental information as well as the applied knowledge which is essential for practitioners, very well summarized in this source. So, what you see in this table, which I have taken it directly from this source. So, for the different reactions involving gases, this is the dissociation of ammonia, this is the oxidation of carbon monoxide. So, in all these cases the equilibrium constant, the corresponding values of alpha and beta are already available from literature. So, one can use those values to calculate the value of, for example, the equilibrium constant. So, now actually now how if we want to see that, we want to change the situation of this equilibrium, for example, then one can actually first of all see that how we can shift the equilibrium to the left or right depending on your requirement of whether you want to enhance a particular reaction species in the chamber or decrease the particular amount of species in the reaction chamber. That one can do that. For example, here it is shown for this reaction of ammonia dissociation, what is shown in this plot here is this y axis q, that means actually the fraction of decomposed ammonia, that means what is the amount of decomposed ammonia which is present. That means you are talking about you started with 1 mole of ammonia and now actually what are the number of moles of ammonia which has decomposed into N2 and H2. So, this is plotted here, this is 0 means entire ammonia is remained as ammonia, no N2 and H2 has formed, and then actually as a function of temperature, and then it starts to dissociate, right. So, as you can see that here these values are given for the total pressure of 3 values. You have 1 atmospheric pressure and less than that and more than that. Okay. So, now if you see that for any given temperature, for example 400 Kelvin, okay, if you see that the fraction of the ammonia which is available as dissociated is given by these values. As one can see that by increasing the pressure one can reduce the amount of ammonia that has been dissociated. That is how one can change the equilibrium of this reaction at a given temperature by playing with the pressure of the system. So, that is how one can control this. So, what one can see that at a normal temperatures of interest which is usually applied in the field of nitriding, that is usually in this range 450 to about 580. Okay. This is the band of temperature where we want to do the nitriding treatment. Okay. This is the temperature where usually one carries the gaseous nitriding. So, if you look at in this window, okay, as you see that from these values, if you say that we are operating at 1 atmospheric pressure, more than 80% of ammonia has already dissociated. That means in your if you are using ammonia in the reaction chamber for nitriding, the thermodynamics predicts that at a given temperature you will have largely a decomposed ammonia. That means you will have large amount of N2 and H2 in the reaction chamber. So, now this kind of knowledge about ability to tune the equilibrium to actually change the reaction directions is very much useful, although most practical processes operate in a non-equilibrium state, but this works out as a very good tool to change the direction, okay, of your reactions. So, now looking at this kind of a reaction equilibrium where all the species involved are gases, but as we see that in the purpose of this course is about where we want to introduce some components of the gas phase which are usually interstitial element like nitrogen or carbon into our solid samples. That means we need to know the solid and the gas mixture equilibrium. So, now if we consider the nitriding, so if we want to use a gaseous nitriding, with N2 gas. Okay. First let us see, because if we look at into the nature, the most easily available source of nitrogen is N2 gas. So, can we use that in order to introduce nitrogen into the samples like the work pieces. So, now actually how we can understand this reaction equilibrium. For example, if we write this reaction equilibrium of N2 gas in equilibrium with the solid having dissolved amount of nitrogen. So, this reaction implies that 1 mole of N has been dissolved into the solid. So, this square bracket implies that this nitrogen is now in the atomic form, but it is in the solid lattice. Okay. So, now in this reaction, so what if we want to write down what is the chemical potential of nitrogen which is in the dissolved state in the solid. So, if we want to know that, that is given as chemical potential of nitrogen in the solid is given as half of chemical potential of. So, I would switch back to this with the terminology which we have used in the previous slide, that is with a, this is G bar, that is the chemical potential of nitrogen in the solid is given as half of N2 gas chemical potential. So, this if we elaborate this with respect to the reference state, this will be half of G naught of N2 gas plus half of RT ln P N2 by P naught, again assuming ideal behavior for the molecular nitrogen gas. Now, what one can see is that in order to have different values of this chemical potential, as you see that once you fix the reference state, the value of this is constant. The only way you can change the value of chemical potential of nitrogen in the solid by changing the partial pressure of or the pressure of nitrogen, because there is no meaning for the partial pressure here because it is only the N2 gas. So, by changing the pressure of N2. For example, if you have 1 atmospheric pressure of N2 and you have chosen the reference state for the N2 gas as P naught as 1 atmosphere, then this is ratio is 1. So, this term drops off. So, that means chemical potential is simply half of G N2 naught of gas. Now, actually why we are looking at the chemical potential of the nitrogen in the solid. So, I will now briefly explain the how we impose the chemical equilibrium between the different phases. For example, we have a solid. Now, I consider here for simplicity it is a iron with some amount of nitrogen in it is in equilibrium with a gas, okay, which is simply the N2. Now, if you want to understand this equilibrium, now this equilibrium can happen between this gas and solid at some particular value of amount of N which is dissolvable in the solid. For example, when we looked at into the gas phase reactions, we have also seen that when it is in equilibrium, the composition of the gas mixture is constant. Now, the equilibrium also fixes what would be the composition of the solid at the equilibrium. Now, how we get that? That we can get it, for example, at a given temperature comma pressure. So, that means at a constant temperature and pressure. If we look at the Gibbs energy, this is the Gibbs energy, for example, of solid, okay, which we are plotting, that is of iron nitrogen solid, that I will, because that means I need to plot this for different amounts of nitrogen, that is where I use the x axis as the amount of nitrogen being added into that. So, this point represents the pure iron, somewhere here we will have the pure nitrogen. This is varying from pure iron to pure nitrogen. What we are plotting is the fraction of nitrogen which is increasing in this direction. So, this will have, let us say this is the Gibbs energy of the solid which has been plotted as a function of nitrogen. Now, the Gibbs energy of the N2 gas, okay, that will be, because the N2 gas in this case is a pure N2. So, this has no composition dependence, but for a given temperature and pressure it has a unique value. For example, that can be anywhere on this axis, right. So, now N2 gas is a, N2 is a very stable molecule. So, because of that it will have its Gibbs energy quite small, they are largely negative. Okay. For example, this is the Gibbs energy or the chemical potential of the nitrogen in the, for example, the gas. Now, for the corresponding value for the solid, how we can get what would be the amount of nitrogen this solid can have at this temperature and pressure. For the chosen this one, we construct a common tangent. When you make a common tangent, this point gives you what is the equilibrium amount of nitrogen that can dissolve into the solid iron for the given gas at a given temperature and pressure. In this case, it is N2 gas. So, now this value, if you want to increase at equilibrium, the possibility is to change the value of chemical potential of nitrogen in the outer atmosphere. So, this also belongs to now Gn of solid, okay, G prime of nitrogen in gas or G prime nitrogen in solid. For example, by, as we can see here, by increasing the pressure of N2, we can change the chemical potential of nitrogen. That means, for example, we choose to this value, okay. Then if we make a common tangent, now this is the equilibrium solubility of nitrogen, which is higher than before. So, this is actually where we are increasing the pressure in this direction for the N2 gas. That is how in principle you can try to change the amount of nitrogen which is dissolvable in the solid. But when we look at the phase diagrams, it is not that always only the solution phases develop, sometimes we develop some compounds. For example, iron and nitrogen has some compound and that has its own Gibbs energy, and that is given by, for example, this is actually representing the Gibbs energy of, let us say, some nitride, iron nitride. Now, actually if you keep on increasing this, at some point of this one, you will also see that you will only you will also stabilize such nitrides into the solid phase. So, this is what is actually that it says that when you impose such a pressure of N2 in the outer atmosphere, your solid will be now simply the iron nitride, okay, some iron nitride. So, this is how actually we can try to have different iron nitrogen phases being synthesizable using the changing the nitrogen pressure. So, now if we look at actually when you use actually the 1 atmospheric pressure nitrogen in the actual situations, what is shown here is the phase diagram of iron and nitrogen. Yeah, you have a temperature as a function of nitrogen content, and it provides what are all the equilibrium phases of this system and what are their compositions at a given temperature and pressure combination. This was the diagram calculated at a pressure of 1 atmosphere. So, these diagrams have been obtained by calculations using thermocalc software. So, this software has all the thermodynamic concepts already encoded, so that it works on the thermodynamic methodology, and it using the database TCFE9. Okay, this is what used. So, this is actually when we impose a pressure of 1 atmospheric nitrogen on the solid iron. Now, at different temperatures, what are all the phase combinations can come. What you see here is this is the BCC iron phase, and this has a solubility within this nitrogen can dissolve. Now, this is the maximum solubility in this phase, that is about 0.04 or so, yeah, that is in the mole percent. Now, as we discussed in the previous slide, if we increase the pressure of nitrogen in the outer atmosphere, let us say in this case we go to 100 atmospheres, then you see the drastically enhanced solubility of nitrogen in the BCC iron. Yeah. So, you can compare these values here, now it is coming close to 0.1. Yeah. So, now other than that, what you see is that the moment you surpass the solubility, then you see that you will form simply the BCC iron is in equilibrium with gas, that is N2 gas. That means, if you have a, if you place a pure iron piece in the into a furnace atmosphere maintained at a constant temperature with a 1 atmosphere or 200 atmospheres of N2 pressure, you will get some amount of nitrogen dissolved in the BCC iron, and then you will have a, that is all will be in equilibrium with the N2 gas. You will not see any of the iron nitrogen phases started to appear here. Okay. Whereas, if you look at actual phase diagrams, which you Google it, that is what you get for the iron nitrogen, that shows, okay, do not focus on this part of this slide, you just concentrate on this phase diagram here. This is also iron nitrogen phase diagram, and here you see that there is a significantly higher solubility of nitrogen in the BCC iron, as you see here in the BCC iron field, and then you also have the iron nitrides being shown here. These are the iron nitrides. So, now as you see that in the previous phase diagrams where we have used N2 gas, we have seen that they are stable phase diagrams, and now these phase diagrams are metastable, because all these iron nitrides would like to decompose to N2 gas and solid iron. So, now still we are able to synthesize iron nitrides. So, that is only possible by using ammonia gas. So, now in the next lecture we will look into the details of how that is actually serving as a better nitriding agent than N2 gas in realizing practically the nitriding of the steel. Thank you.